Namaste dosto. Imagine you're playing cricket and the ball is flying towards you at a certain speed, heading at an angle. How do you describe this exactly? Well, you use a vector. A vector is a special kind of quantity. It has both magnitude and direction. Think of it like an arrow pointing the way, with a length that tells you how much. We usually write it as a letter with an arrow on top, like vector A. Vectors are everywhere in maths and physics. They help us describe forces pushing or pulling, velocities showing how fast and where something's moving, and displacements telling us how far and in which direction someone or something has moved. In notation, vectors may appear as bold letters, like A, or with an arrow above, like vector V, vector R, all pointing to the idea of a quantity with direction. Now, scalars are a bit different. Scalars are quantities that have only size, no direction at all. For example, your weight or the time elapsed while playing cricket are scalars. They just say how much, not where to. Temperature, mass, and time all belong to this simpler category. So remember, vectors combine how much and where, while scalars only tell us how much. We're off to a great start understanding these building blocks of vector algebra. Coming from that, let's talk about two very special kinds of vectors, the zero vector and the unit vector. First, the zero vector. This is a vector that has zero magnitude and no specific direction. Imagine an arrow with length 0. It's basically just a point. We write it as vector 0 or 0 with an arrow. In calculations, it works as the 0 in addition. Adding the 0 vector to any vector leaves it unchanged. So, for any vector a plus 0 vector is still A. Next, unit vectors. These are vectors with magnitude exactly 1. Think of them as pure directions without any scaling. They tell you which way, but not how far. To find a unit vector along A, you divide vector A by its magnitude, written as unit vector equals vector divided by magnitude of vector A. This normalizes A to length 1. In Cartesian coordinates, we use the special unit vectors I hat, j hat, and k hat for the x, y, and z directions, respectively. Any vector R can be written as x times I hat plus y times j hat plus z times k hat. This breaks the vector into its components along each axis. So zero vectors remind us of the additive identity, and unit vectors help us specify direction clearly. Excellent. These special vectors make algebra much cleaner. Now, let's look at how vectors are positioned geometrically. Starting with coinitial and collinear vectors. Coinitial vectors are those that start from the same point but can point in different directions or be of different lengths. Imagine the hands of a clock at different times. Their vectors all begin at the center but point differently. Collinear vectors, on the other hand, lie along the same straight line. This means one vector can be expressed as some scalar multiple of another, written as vector A equals k times vector B, where k is any real number. If k is positive, the vectors share the same direction. But if k is negative, they point opposite ways. Understanding collinearity is very important, especially in physics problems about equilibrium, where force vectors need to balance along lines. Knowing if vectors are collinear helps simplify the analysis. Now, can you picture two vectors lying exactly on the same line, maybe opposite or along the same direction? That's collinearity. Great. Next, let's understand when two vectors are equal or negative of each other. Two vectors are equal if they have exactly the same magnitude and direction, no matter where they start. Mathematically, vector A equals vector B if and only if their magnitudes are equal and their directions coincide. Negative vectors have the same magnitude but point in exactly opposite directions. If you add a vector to its negative, you get the zero vector, basically cancelling each other out. This is written as vector A plus negative vector A equals 0 vector. These ideas are foundational for vector subtraction and understanding how vectors combine or cancel out in space. So remember, equal vectors are twins in size and direction, but negative vectors are like twins facing opposite ways. Now, let's talk about vectors that describe points in space, position and displacement vectors. A position vector shows where a point is located relative to the origin. If the point has coordinates x, y, and z, then the position vector r is written as x times I hat plus y times j hat plus z times k hat. This tells us exactly how far along each axis we are from the origin. Displacement vectors are about change. They show how you move from one point, say A, to another point, B. This displacement vector AB equals vector ob minus vector OA, where OA and OB are the position vectors of points A and B respectively. If A has coordinates x1, y1, z1, and B has x2, y2, z2, then displacement of is written as x2 minus x1 times I hat plus, y2 minus y1 times j hat plus, z2 minus z1 times k hat. Displacement vectors are key in kinematics, allowing us to describe motion precisely. Can you imagine moving along a straight line from one spot to another? That's displacement. Shabash. Moving ahead, let's explore parallel and coplanar vectors. How vectors relate in orientation. Parallel vectors point in the same or opposite direction along a line or plane. We say vector A equals lambda times vector B, where lambda is a scalar. If lambda is positive, vectors have the same direction. If negative, opposite directions. Coplanar vectors lie in the same plane. This means one vector can be written as a linear combination of the others. For example, vectors A, B, and C are coplanar if the scalar triple product of A with B cross C equals 0. Written mathematically, vector A dot product, vector B cross vector C equals 0. Understanding whether vectors are coplanar helps determine linear dependence and is useful in geometry for calculating areas and volumes. Quick check. If three vectors satisfy this scalar triple product 0 condition, they all lie in the same plane. Got it? Excellent. Let's put all this together with a solved example. Suppose we have vector A equal to 3 times I hat plus 4 times j hat and vector B equal to 6 times I hat plus 8 times j hat. Our task: classify the relation between A and B. We model that if vector B equals k times vector A, then the vectors are parallel and collinear. So let's find k. Step 1. Observe vector B equals 6 times I hat plus 8 times j hat. Notice this is exactly twice vector A, which is 3 times I hat plus 4 times j hat. So vector B equals 2 times vector A. Step 2. This means vector B equals 2 times vector A, implying vectors A and B are collinear and have the same direction. Resultantly, vectors are collinear, equal in direction, but vector B is twice as long as vector A. You just applied scalar multiplication to identify vector relations. Excellent job! To wrap up today's session, let's quickly review the main types of vectors we learned. First, the zero vector, symbolized as vector 0, has magnitude 0 and no definite direction. Then, the unit vector, written as unit vector A equals vector A divided by magnitude of vector A, which only tells direction with magnitude 1. We also discussed collinear vectors, written as vector A equals k times vector B, lying along a common line. Key ideas to remember: equal vectors have the same magnitude and direction. Collinearity implies vector dependence, and coplanar vectors lie in one plane. Now, a quick question for you. If vector C equals negative 1/2 times vector D, are they collinear? Think for a second. Yes, because one is a scalar multiple of the other, but they point opposite directions. That's all for today. Keep practicing these concepts. They're essential for your physics and maths exams, and they help decode how quantities work in the real world, from cricket to rockets. Till next time, keep vectors pointing you in the right direction.